Is it working? Why they cannot have it? Why the camera is not working? Integrated. Now they can use my camera, but not this one. It works?
Yeah.
Okay, so
But it's going to.
okay. Okay. So I don't know if you can see my. Can you see my screen? Can you see my screen?
Yes.
Okay. So now I'm just explaining how this convolutional layer works. So we have an input image. This is the original image, right? And if this one is the original image, and if we decide that we need to get 4 feature maps, we will get 4 from this one, correct? So this is the first feature map. This is the second, third, fourth, correct? So we will apply this one. For this one, we selected the kernel to be 9 times 3 times 3. So this one will have 3. We will have 9 parameters. Each one will have 9 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. Correct? This is omega 1, omega 2, until we have omega 9. The same, correct? Each point is connected to one block, one cell of the kernel size. We will apply this one to the first part. We will make those calculations, multiply those weights with this one, and take, for example, summation average, and we will put the value here in this first Excel. So this one, in fact, could be connected to this one, right? And we have stride equal 1, so this one will be moved by 1 step. We will make this convolution one more time and convolution activation. So you will get the second pixel value here, and you will do this one, correct? Until the last one here, and after that we will go down 1 step, right? So we will move like this. So in fact, we can just say that each feature will create one neuron here, and this neuron will be connected with 9 values. Those 9 values are the 9 parameters of the kernel size, which is 3 times 3. We will apply this one-to-one place, correct? Multiplications, weighted sum, and after weighted sum, we will apply the we will have the weighted sum, and after that we will apply activation, correct? And after activation, we will have a value. This value will keep it here. Using the stride, if the stride equal 1 or 2, we will move by 1 step or 2 steps or whatever. We will apply this one more time to the new one here, correct? We will apply those weighted sum, correct? And after weighted sum, we will apply to the activation. We will get a new value. This value we will keep it here. We will repeat this one until we get the first feature map. The same, the second layer, it will do the same, correct? This one also will connect 9 values, correct? So this one is connected to a kernel. We will apply it to, sorry, kernel. Oh, sorry, kernel. ايه عمر حاجة؟ ها؟
Yeah. Yeah.
Yes. So we will do it like this one. So how many neurons you will have? Number of neurons will be the number of feature maps what you want, and each one is connected. So the second one will be connected to the second feature map. We will get those fixed values in each iteration. So we will make one first iteration. We will get some values. We will repeat those iterations until we get something that has a meaning effect, right? You will not put those feature maps from the first iteration. We will train our model for number of iterations, number of blocks. So you will repeat this several times until your model is trained. Your model will be trained when those weight values, because each time you adjust those weight values. So at some point, those weight values will be numbers which will make some, which will generate meaningful feature maps. So layer by layer. So therefore, when we calculate number, so how many number of parameters here now? If we need, for example, for one layer, one convolution layer, how can we calculate number of weights, number of parameters? How can we calculate it?
Like the previous one.
So
yeah.
yes.
The multiply.
Can you give an example? So for example, we want to get 64 feature maps. The size will be 3 times 3 kernel size. So how many parameters we calculate for the convolution layer? So if this is the first convolution layer, and those are the parameters.
65 multiplied 4?
No, yeah, it will be 64 multiplied by this one. 1. This is the kernel size by 3 times 3.
Yeah, 9. I thought
plus
4.
60. Yeah.
64.
Okay.
Yeah.
I will just use it. So the size here, parameters of this it will be 4. We have the size will be this one. So number of parameters will be 4 times 3 times 3 plus 4. Correct. So it's 4 because those are the number of features which we want to extract. Feature maps. So imagine that it's 1 neuron for each one. It's exactly like this, 1 neuron for each feature map, and each neuron is connected with 9 parameters. Those 9 parameters, it's the kernel size plus 1 because each one is connected with a bytes. Correct? Each one of those has a bytes value. So number of parameters will be like this. So this is how we calculate number of parameters. So in convolutional layers, we don't care about the image size. Correct? Because I don't care, because if the image size is different, it will make difference for number of activations. But of course, in neural network, it must be fixed. Right? So the kernel size here must be fixed.
I just searching about something about sigma space. I think there is a procedure when a model is building about a space, a sigma space. And when we use strides, maybe there is something embedded in the model in order to find that section of picture has a lot of sigma and
what is sigma?
Sigma space. Each picture and each section of picture has different sigma for normal distribution. There is a pure mathematic formula here about, for example, there is a procedure in the model to find those sections as a high sigma. And I think that is following that.
But I don't know what is sigma. Sigma, is it something from image processing?
Yeah, I think in the model. But just research about that because yeah.
But I mean, just simply, I mean, you have this stride that will control the overlap, how much overlap between each scan when we are scanning. We will go if you go one step.
Yes, I know the concept, but how it works exactly.
What?
How it works? How to, for example.
How do you move?
Yeah.
The kernel?
Yeah.
It will just move step by step.
Just move?
Yes, from left to right, and from top to, so it will move like one step, and after that will go down, one step, we repeat it. Right? So if for example here is a stride, in this image is a stride equal 3, for example. So in this case, we will take the first one here, and after that, we will move 3 steps. So we will move here, correct? The second time we will go here, and so on. So it will be like this one. Next time we will go back here, correct? So scribe, it's calculated, it's controlling the amount of overlap, for example, which, because there are some places which we need to scan several times. I mean, if n equal 1 here, we will, and n and the size is 3, means some places will be scanned 3 times, right?
I will, for example, in my opinion, and I read about that on the internet, some section of each picture has more information and features than other sites. And I think, for example, some asteroid is related to something like that. And, we have to, for example, asteroid by finding those sections. I don't know how, but I think something related to that. I hope you get what I'm saying.
Maybe we can, I mean, with time we will try to.
Okay.
Yes. So now this is my first deep neural network, for example. So we will have one layer. This layer will try to extract those representations, right? And those representations, we will feed them to the next layer, and the next layer will be the same structure, for example, with different number of features or different kernel size or different stripe. You can just do whatever you want, and until we get to the last convolutional layer. And in the last convolutional layer, we will have those high level representations of my my features. And you can, as Hussein today he mentioned, if you will define your model as a model using model API, you can get access to those layers. In fact, if you want to block those feature maps, sometimes we need to see, okay, what is the output of this layer? What is the output? Does it have any correlation with the input, right? Is it still vector, right? Because we apply those convolutional or those kernels to extract features. So what are those features? Does those features have any meaning, for example, for the problem which we are solving? Is it still car? Is it still a cat and dog, for example? So we don't know. So if you want to check this, you can, if you define your model as a sequential, it will be difficult to extract those intermediate values and plot them. But if you can define your model using model API, it will be easy, because when it's model API, you just need to define the input layer and the layer which you want to extract. So the output will be maybe this one, or maybe the output will be this one. In this case, I can get those intermediate values, and I can put those values if you want to see how they look like. And this is the same which I did in fact when we trained autoencoder. Because autoencoder, it was the same. We have an input layer. Some layers will have a bottleneck, and we have the decoder, right? So I'm interested in plotting and extracting the code, for example. So in this case, I need to define an encoder as a model. The input will be the input layer, and the output will be the bottleneck, correct? So in this case, I can extract. This is how I plotted it in the slides, if you can still remember. So you have some image, you have the code, and if you want to even use a decoder, you can define the decoder as a model API. In this case, the input will be the code, and the output will be the constructed image, right? So when you are working with model, you will have more flexibility. When you are working with model API, and we will see next week if when you run it, if there is difference in computational time. We need to check this.
Okay.
Yeah. So, and finally, we will have those higher order, high-level features. We will feed those high-level features to the fully connected layer or 2 fully connected layers, and finally we will have a decision here, right? So I mean, how deep learning works, it's the same. I mean, it's the same as we have some layers. Those layers will make data transformations. We will make some predictions. We have some predictions. We have some true values classes. We will calculate the loss function. We will try to use an optimizer to minimize this loss function. The optimizer will try to adjust those weights in a way to minimize this loss function, right? And this is how we train our models. In adversarial attacks, as we mentioned last time, you will have also a loss function, but we need to maximize this loss function, not minimize it. Correct? So in fact, when we minimize this loss function, we try to adjust weights in a way to minimize this one. So we use gradient descent. If you try to find the noise which we need to add to the input image to make the model confused, we use not gradient descent, we use gradient ascent. Correct? So we need to find the values which will maximize this or not minimize them. Because we want to make our models confused. This is an example with MNIST. So here I used sequential. It would be nice really, because next time I will maybe for this example also I will try to use model, right? Because it's exciting to make comparisons between model API and sequential API. Here we used how many convolution layers? No, it's a shallow learning in fact. This one is just shallow learning. So it's dense layer. Dense layer, it means just normal, it's no convolution. So dense layer, and it has 512 outputs. Activations are A in U. The input shape, we need to define the input shape. It's 28 times 28, right? And it's when it's 28 times 28 means we flatten the input. So you have some image, you will flatten it. So it will be one vector, which is 1 times 28 times 28. So you can just give it a name, for example. So this one is hidden layer or first hidden layer. And I have only two layers. The second, I used dropout, right? Why do we need to use dropout? We use dropout to try to correct. So we try to resist this overfitting and try to minimize the overfitting. So the output layer, we will have 10 classes, correct? So the number of units will be 10. So the activation will be softmax. Why softmax? Why softmax? Huh?
Classify one image, either 0 and 1. And,
yeah, you can say it's binary classification or it's multi-classification effect. So this softmax, it will give us probability, correct? Yeah. The probability that the image belongs to, when it's 4, the probability that it will be that it is 4, and the probability that it is 0. So it will be probability we need to use softmax. And we will use the loss function. It will be categorical this cross entropy because we have 10 classes. So we need the. So the model will be like this one. So the input size will be 28 times 28, which is 784. The input layer, it do nothing, just to transfer input to output. Correct? It has no parameters, it do nothing at all. And the hidden layer, the first hidden layer, the input will be 784, the output will be 512. The output layer, the input will be 512 because we're connecting, correct? And the output will be 10, right? The dropout, it has no parameters. Dropout has no parameters. So if we want to calculate number of parameters here, how can we calculate it? Number of trainable parameters, so it will be number of parameters.
That number multiply
this one plus
the number of neuron and data.
This one, okay, and here also it will be 10 times this one,
yes,
plus 10. So it will be this number of trainable parameters. I just trained this one, and I'm testing it with predicted and tested data set. So we will have this accuracy. So the accuracy looks very high, right? Yes. And if you want to get the total or overall accuracy, you need to put it in your code and define it. So I just tried to also here to plot intermediate values, correct? So I defined here a model. Yes, I used it here. Right? So if you want to print out, if you want to display intermediate values, you need to use model API. So in fact, here I use the model API. The input will be the model input because I defined the model as a sequential. So the input for this one, it will be model input because it has been defined already. And the output will be, we can use this nice command here, get layer, right? Get layer, and just to define the name of the layer or the number of the layer, right? So I want to get the output from the first layer, so it's layer 1 in fact. So you can just say it's get layer 0 or hidden layer, if you can give it a name. Because we have 2 layers, 1 and 2. So the numbers, the index of the layer could be 0 and 1. So if you want to get plot the output from the first layer, it should be layer number 0, correct? So it will be like this one. We decided this one, I know the size here, it will be 512. So just to try to make it squared and plot it as an image, right? And I just need to predict. So I defined a second model, temporary model, just a temporary model predict for some inputs. So I provided this one as an input, and this one will be the intermediate out from the hidden layer, and this one will be the output. So in this case, we can so I have the y predict. This one will be y predict model dot predict, and intermediate model dot predict to get this one. So it will be like this one if you want to plot it. And as you can see here, there is no connection. I cannot understand anything from this one. Correct? It's some values which I don't know. I mean, it's hard for us to understand what does this mean. But maybe if you are using deep learning, you can extract features. Maybe those features will have a meaning. Correct? So if we are solving the same problem using deep learning, and we try to plot high-level features, for example, from the last convolutional layers, maybe you can see some correlation between this one and the other. Right? Because also from the machine point of view, this one has a meaning for the machine, but not for us. Right? So it's not very important to get something looks like the original image, but this is how can we do it. So we use the Hill model, ABR. We use the sequential and we use the model. We use sequential when we are training a model from end to end. But if you want to plot those intermediate values, we can just use model KPR for getting access to some layers. This is very, very important. Very, very important. If you are working with the GAN, for example, and I want to plot some outputs, if you train simply autoencoder, because autoencoder we use it for dimensionality reduction, and we're interested in the intermediate values or the bottleneck. So I talked about this one last time. How can we, data batching, for example. I guess I talked about this one last time. So you have, for example, if you have a batch size of 128, how can we make this data batching to make modeling the training simple? So for example, so if you want to split your data into batches, for example, this is my X-train, and I want to divide it into a number of batches. How many batches we will get? Right? So yes. So how can you get those batches, for example? So it will be X-train. You need to split it into a number of batches. Yeah. So you will divide the length of this data set by the batch size. So for example, I have 10,000 images, and I want to divide it into a batches. The batch size will be 128. Right? So a number of batches will be the length of the data size divided by the batch size. Correct? Yeah. So in this case, I can find how many batches. So in this case, we'll get number of batches. Time series or sequence data, how can we work with this one? So when you have one time is matter, you need to consider time. So I have here an example. For example, it will be stored in 3D tensor. When time, this is very important when you are working with a time series. Time series, there could be numbers, there could be images, right? So images also could be a time series. Yeah. Because I can have a sequence of images, and I need to keep this order. And then when you are splitting, you cannot just split as we did with images in the set. We shuffle and we split. No, when it's time series, we cannot shuffle the data set. Very, very important. So the first part will be for training, the last part will be testing or vice versa, but you need to keep the order.
You need to shuffle.
When you shuffle the data, like MNIST, for example, or 50 data set. For 50 data set, it's a data set for face recognition, and there is 10 images like this for each person. In total, it's 400. So if you will, I need to shuffle it to be sure that all people are equally represented in the, all classes are equally represented in the training and testing, right? Because I can train my model with us, for example, and I want to test it with Hamad, for example, online. So the model will not be able to optimize them if we will divide it like this, right? Yeah. But we need to shuffle all of us, and some images will be used for training, so the model will understand. We will see those images in the training phase, and the rest will be tested. So in this case, we will get results which is reliable. So we shuffle when time is not important, but when time is important, you cannot shuffle your data set, right? So we need to keep the order. For stock market, for example, so I have the data from 20 years ago, for example, in order: 1998, 1991, 82, and so on until today, for example, 30 years, for example, or 40 years. So in this case, we need to keep time, we need to keep order. If you shuffle it, you will destroy the time impact or the time effect. You must keep it as it is.
Because of the connection between each table.
Yes, yes. So we need to keep the order. Because I mean the values of the historical values from last year's the impact. We got COVID for 1 year, for example, so it will impact the situation. If you will shuffle it, you will destroy those interdependencies, right? We need to keep it in the same order. So when you have, for example, time series data, you can put it as a 3D tensor. One will be just for the order. So for example, data set of stock prices. Every minute we store current price, highest and lowest price in the past minute. In each minute we store 3 values, right? We have the current value, highest value, and lowest value, for example. So thus in each minute we have how many values? We put it in each minute, for example. So in this case, for the entire day of trading, it would be 6.5 working hours times 60. So we'll have 390 values for each day, right? So we can put it as a 2D tensor like this one. This one will be the time. This one will be the 3 values which we store in. It will be 390 times 2D tensor, right? Because I have 3 values which we are recording each minute, and per day, the working day, it will be 390 values. If you want to keep this values for an entire year, if we need to keep this value for the whole year, for example.
Yeah, okay.
So in this case, we will store it as a 3D tensor, and we will specify the first dimension for number of days. Per year, for example, we have 250 working days per year. So in this case, this one will be by day, starting from 0 until 365, for example, correct? So this one will be for the day, this one will be for the minutes per day, this one will be the values which you are registering, for example. If you have 10 days, 10 years, for example, or 20 years, so we can have 4D tensor.
Sorry?
And so on.
Do you have any, for example, on Excel or something like that to show about each sensor? For example, you are talking about the first parameter. The first section is about day, the second about minute, and the last one about
Yeah, because I mean this is the dimension of the vector, right? The dimension of the vector. So I have 3 values which I need to keep each minute, right?
Yeah.
I have 3 values. So we need to add one more dimension for the minute.
Yeah.
Correct? Per day, for example. And if you want to have record for the whole year, for example, so in this case we need to add one more dimension. Right. So those are the values which we need to keep, right? This one for the minute, this one for the day, this one for the year. Correct?
Yes.
So in this case, I can get access to any value at any point. If you want to get access to some values, but the values, the most important values here are those values. This is the order, right?
Yes.
So if you are building a model, you just try to predict those values. Current value, minimum value, and highest value.
So the first values are only for identification. To know that, okay, this is actually this one.
Yes.
This is this one.
Yes. So you need to specify which day, which year, which day, which minute. You can just go to those, like indexing. So
You keep the index.
yes, we keep the index. And in this case, the order is important. So I cannot shuffle the data as we usually do in classification. Because when we have a model data for classification cats and dogs, we shuffle it in classification. Here also, it will be, here it will be prediction, right? We are predicting, right? So we need to keep the order.
I don't know if that is more than 3D tensor. Yes?
Yes. That will be 4D tensors, 6D. I mean, it's as you want. It's not just, I mean, you can configure it as you want. So for example, another example, we have a data set of tweets where Twitter, data set from Twitter, for example, where each tweet is a sequence of 280 characters. I mean, in Twitter, we have maximum 280 characters. So you can write your message with a maximum limit of 280 characters out of an alphabet of 128. And in English, we have 128 characters. unique characters. So it is the digits from 0 to 9, lowercase letters A to Z, uppercase letters A capital to Z capital, and the punctuation symbols. So in total, it's 128. And in Twitter, for example, maybe we limited it to 228, 220, just to make it easy for machine learning to understand things about people around, right? Because now it's limited. And they make it up to the user to select the most important. If you want to deliver the message, you need to make it short. And we have total, or in maximum, it will be 218. I mentioned last time the examples for this internet database for movies, right? So it's up to everyone to write his review. So, but after that, if we said, okay, we need to select a dictionary of the most popular 10,000 words, we will ignore many words, many things from the review, because we will just use the most popular words to represent it. So in this case, we are ignoring many things. It will be hard, in fact, to understand the review. I mean, what is the mean? Is it really positive? Is it negative for sentiment analysis? Is it positive? Is it negative? But in total, for example, when they put this limit here, they just make it's up to each user to just select the most important words to describe this. Now it's fixed. The size is fixed, which makes it easy for machine learning to process it. So maybe the idea behind this was to building something which is easy for processing later on. It's not up to each user to just select the length, but once the length we have maximum length. So for example, so now each tweet is 280 letters or words. In this setting, each character can be encoded as a binary vector of size 128. Correct? Because the maximum, the maximum number of characters is 128. Correct? So in this case, we can just represent each it has 128 characters. We can represent it as 228 times in binary. If we will use one hot encoding, so it will be 280 times. It will be 280 times 128, right? Correct. So in this setting, each character can be encoded as a binary vector of size 128. All zeros except where the index corresponding to the character. So each tweet can then be encoded as a 2D tensor of 28 times 128. Correct? So now so do you see? So when they limited it to 228, they make it easy for processing by machine learning, for example. Because now we can encode each tweet into this tensor, 2D tensor shape, for example. For example, a data set of 1 million tweets, it will be in this 3D tensor. 1 million times 280 times 120. So in this case, it will be easy for data processing. So for images, for example, images, it's also easy. For example, images usually have 3 dimensions. If it is an RGB image, we have the height, width, and the color depth. A grayscale image, it has one dimensional color channel, so it will be just 28 times 28. But if it is RGB, it will be 28 times 28 times 3, because we have RGB, the color channels. A batch of 128 grayscale images of size 28 times 28, it could be like this one. So the batch size is 128. So it will be 128 times 28 times 28 times 1, because we have only one color channel. So the format would be sample, height, width, color depth. So this is how, if you want to prepare your data. A video, it will be the same, because the video consists of frames, right? So the frame rate will give you, so each frame is a RGB image. Each RGB image, it will be height, width, times color depth. But how many frames?
56.
Yeah, so it could be more, right? So it's a number of frames per second. We need to decide how many frames per second, because at the end it will be number of images, but in sequence, in order. Because if you need to display it as a video, we need to keep the same order. You cannot destroy the order by shuffling it. If you shuffle it, if you are tracking a person in frames, we need to keep the order. I will train my model to recognize him in one frame, and I will track him in the next frames. You can track a person in different frames, for example. This is how Chinese they making cameras everywhere, and they train models to learn features of a person from some frames, and they can track him in different frames, different cameras, different locations, right? And they can find a trajectory, and they can find his trajectory in the city first. So 60 seconds, and if we have 144, okay, so if we have 60 seconds of YouTube video of size 144 times 256, a video clip, we have 4 samples per second, 4 frames per second. So in this case, we will have 4 frames per second, and it's 60 seconds. So in total, we will have how many frames? It will be 4 times 60, which is 240. So we have here 240. And each image is 144 times 256 times 3, because we have 3 colors. So in this case, the batch, if we have batch of 4 such videos, it will be stored. So if you have 4 videos, each video is 60 seconds, it will be 4 times 240, 4 videos, right? So it will be stored in 5th dimensional tensor. So in total, if you want to calculate memory size, because memory size is very important. Memory size, it should be connected with the batch size, right? Because if you go for 128 batches, batch size, for example, is it possible for one GPU memory, for example? So sometimes it's very important to check the memory size. So for example, in this case, if you will go for a batch size of 4 of such videos, how much memory we need? So in this case, you will just multiply all those numbers, correct, together, and each, so we'll have this number of values or pixel values, right? But what is the size of each? What is the memory size of each pixel, right? So this is the total number of pixels. When we multiply all those numbers together, we will get the number of pixels.
So if you want to find a person, say in a feed camera live, you have to first train a model on previous videos of that person, then run this model.
Yes, you know what? You know what? You need to check, because maybe he has a hair, he will take it out. So he will lose. If you're building some model which is not smart, maybe you will lose him if he removes his hair, for example. He's wearing a jacket. We'll just take the jacket out.
But we're going to use a pre-trained model on the live feed camera.
Yes. For example, I guess they're doing it like this. We use number of frames for training a model, right? So now I train these features from the back side or from sides and stuff like this. And after that, I will use this one for object detection. It's object detection, correct? But I will detect him in other things, right? So you will localize him in the image, because in the image you have many people. If it is an airport, for example, you have thousands of people just moving. What you train is his shape and his structure, how he is walking and stuff like this. So you trained already, you collected number of frames, because someone's saying, okay, this is the guy you should want to track. You just collect some images, he will train a model using those images, and he will track, and this one will be used for tracking in the rest of the images. Of course, you can by yourself to look into all frames to take each. Right? Now I train a model. The model will learn as much as possible from his features, how he is walking. Maybe you have in some things, as you mentioned, maybe you take a jacket in some things. You're trying to collect number of frames to get much information as much as possible for that person. So now the model will be trained. I will use this model to localize them in the rest of the images. In the rest of the images, there will be animals moving, cars, other people walking beside him, but you will try to localize them in the image. And the frame by frame, you can just find, and of course they have huge movie systems, lots of cameras everywhere, so you can just track him in the whole city and find his trajectory. Right? Maybe also they have somewhere to predict. Because if you can track him, maybe you can predict what will be the next step, next bus stop, next train station, for example. So now we need to calculate how much memory we will need. So just multiply all those numbers, we will get this big values. It's number of pixels, correct? But how can we store a pixel value? If you will store a pixel value in 32 bits, for example, if it's a float 32, It means I will store it in 32 bits. 32 bits means how many bytes? 4 bytes, correct? Because each byte it's 8 bits, right? So now I'm 4 bytes, just to divide this number by 4. So it will be 4 bytes, just multiply this number by 4 bytes. When you multiply it by 4 bytes, you will get this number of megabytes, right? 425 megabytes to store this tensor. So each batch, so imagine that this batch now is for 1 minute, 1 minute big effect. And resolution is not that big, in fact, 144 times 256. So the resolution is not that big. So how much memory for the batch size? It will be 425 megabytes. If you have 8 megabytes, if you have 8 megabytes, your GPU memory, for example, so you can decide what will be the batch size for training your model, because I want because in batch size we're working batch by batch, right? So in batch, mini batch training, for example, so we have the batch time and we are working batch by batch. So this is very important. So if you have a problem in GPU memory, for example, maybe the system will ask you to reduce the batch size. Why reducing the batch size? Because when we reduce the batch size, we will reduce the memory required for storing this tensor. Because we have this is the memory which is required to store this tensor in my RAM. Calculating also, because we are making some calculations. So number of calculations, we need memory. So if you are lacking memory, you need to reduce the batch size. So you can go up with the batch size. So it's according to the memory required for storing this batch size. So this is very simple example to make some calculations. You can just find how much memory we need, for example. So it would be nice because when we read papers, for example, when they are talking about those, how much memory is required for this, for example, it looks very professional. Weights, because also in the memory also we need to store not only the batch size, not only our batch of data sets, for example, but also there are many other variables, in fact, which we need to store. We have number of calculations, we have model parameters, you have 1 million weights, for example, how much memory, correct? So you can calculate how much memory is used for data, how much memory is used for training your model, and so on. Yes, so this is another example. It's this video database. It's internet movies database, and it's for just reviewing, and it's working with text, which is very, very important. So, so this dataset consists of 50K movies reviews, and it's used for natural language processing, and it's sentiment analysis. So the output, in fact, it's positive and negative. Some positive movies and negative movies. Just make it easy. If you want to make it multi-class classification, you can just say this is a new drama. So you can divide it into some classes. But sentiment analysis here, it's very simple. It's just plus and negative. So the input to the model will be a text, and the output will be plus and negative, correct? Or plus and 0 to 1. So it's positive movie, negative movie. People like it, people don't like it. So of course, this one it's labeled. So the input will be a text, the output will be negative, positive, and so on. So some people they read those, went through those reviews, and they just rank it, right? For label it or something. Yeah. Why you giving me too much? So can I answer my question? Can I answer?
Yeah.
Yes.
işler ayarlar.
Yes. So this one also, we cannot work with text as text. We need to convert, we need to code it, right? We need to put it in, to convert it into a code. We need to convert it into numbers because machine learning cannot work with text. So each review is a sequence of words of different lengths because each one is different. Someone is just writing a lot, someone is just very short. So we need to convert it into something fixed size. So if we will use a specific word in the dictionary, we can just select top 10,000 most popular words. We can rank them in natural language processing. We can count words, and we can see the most used, most popular word in the text, right? So you can do this one, and you can select the top 10,000 words used in the text, and you can just make a dictionary. So we can have each word with an index. We can just sort it from 0 to 9,999. Each word will have as an index, correct? So in this case, in fact, we can convert each, we can just limit it to the top 10,000, right? So imagine you wrote 2 pages, but this 2 pages of reviews, we will see how many words has been used from this. We will just filter it. We will just pick the most, the top 10,000 words which are used, and we will convert each one into its code. We will convert it into index. So we'll have a vector, and this vector consists of 10,000 words, right? We will just replace each word by its index, and we will put 1 in that index and 0 other words. So each review sequence of words will be converted into a vector of 10,000 dimensional vector of 0 except for word index. So the dataset will be represented as a 2D tensor. This one was 50K, so it will be 50K times 10,000. Because each review will be converted into a vector of 10,000 values. So now we will convert it into this one. This one, it will be just zeros except 1 how do you call it? It will be 0 everywhere except 1 at the word index, right? So in this case, we have the data set. We can download it from Keras datasets, IMDb, and we will restrict number of words to 10,000 most popular, most frequently occurring or used words in the data set, and you can just start playing with it. Now we are converting it into X chain, Y chain, X test, Y test. You can just, now it's numbers. So now you can train a model. So the input will be a vector of 10,000 values, and the output will be, we will have 2 outputs, maybe plus and negative, or just 1 output. It could be 1 and 0, for example. 1 when it's positive, 0 when it's negative. So you can convert this positive and negative into 0 and 1, for example. So the result will be 1, for example. When it's 1, it means it's positive. When it's 0, it means it's negative review, right? So now we can build a model which will be trained with using this internet movies database. So now we can work with text. So it will be something like this one. So this is a review, for example. This is a text, correct? And now we are replacing each word by its index, right? So this one maybe it's 1. Maybe film, it was number 14 in the dictionary because we have a dictionary of the most popular 10,000 words. So we can start with this. Maybe it's 1. Film is 14. Was is 22. We can search for another was here. Is there any other was here? So
In the 10th one.
10th?
Check there was a
1, 2, 3, 4, 5. Where?
going.
Okay, 10th. Okay, but I don't know. Is it maybe this one? Maybe, correct?
Yeah.
This film was 22. Yes, it's 22. I don't know if it's, but anyway, each word has a unique index, right? So now we are converting this one into this index, right? The size here will be the same as the size here. This one is from 10,000, it's the index. From 0 to maximum 9,999. But the size here, number of elements here, will be the same as the number of rows here. So we cannot use this one for training a model, in fact, because the size here will be different according to each review. Some reviews are short, some reviews are bigger. Now we need to convert this one into a fixed length. So now we will convert this one into a vector of 10,000 values. So this 10,000 values, it will be like this one. It will be a vector starting from 0, 1, 2, until 9,999. We will go to the index. We have the index of 1, so I will put here 1. We have the index of 14. I will put 14, 1. But it's all 0, by the way. By default, all values are zeros, and we will put 1 when it's as the index, which appeared here in the text. I guess, Hamad, you mentioned something last time about repeating words.
Yeah.
So, can you say something about it?
Yes, for example, if we have a tweet, as we are talking about the tweets, and we have a word which is repeated several times. So instead of just turning the bit on, we can put the count of that number up here in the tweet.
Yeah, and then normalize.
Yeah.
Correct. So in this case, it will be float number. Instead of working with binary values, we will have, for example, if you have, for example, film has been repeated 3 times. So we will not put only 1 here, not binary value 1. We will put 3 because it has been repeated 3 times. So now it will have more numbers. Those numbers will represent number of repetition. Maybe that repetition is important because it has an indication of something. So in this case, we will increase some values. It will be the count of, instead of just flipping it into 1, we will have the count of words, count of numbers, which is a word here. But in this case, you have to normalize, right? So in this case, we'll just divide all values by the maximum value, or the range, right? So in this case, this one will be 1, and the rest will be third, for example. All values will be 4.63. So thanks, Hamid. If we are building a model for this sentiment classification, I did it in fact, and the accuracy is 87%, not that much. I just used the 4 epochs, but the model overfilled quickly. So in this case, I will define a sequential model. It will be also shallow learning. We are not using any deep learning. So we will have dense layer. This dense layer, it will have 1024 units. Inputs will be 10,000. So because the input vector is 10,000 values, right? 10,000 values. The number of outputs will be 1024. This one 512. This one 256. Just to make any decision. It's up to you. I used here sigmoid because the output will be number between 0 and 1. Right? Correct? Sigmoid like this?
Yes, yes.
So it will be 0 when it's negative, it will be 1 when it's positive. When it's 0.6, it will be positive. So usually it's number between 0 and 1, and we just try to take round it to the nearest integer type. So I used binary cross entropy because we have 2 classes, for example, and just I'm blocking the training. X training will be all values except I used the first 8,000 values. No, it's 20,000. It's first 30,000 for training, and the last 20,000 for testing. And it will be like this one. So now we can work with text, right? We need to work with text because text is very, very important. If you want for text translation, it's more complex because I have sequence to sequence, right? So the input will be a sequence, and the output will be a sequence. I don't know the size. The size will be different because English is different from French, from Russian, correct? In some other language, you can just use one word and describe the whole story. In some other languages, you need to talk a lot in fact. So it's a sequence to sequence, but the size of the sequence will be different. So can we use this one for translation, text translation, such as a chatbot, for example? When is a chatbot? It's a sequence to sequence. So I will ask the chatbot, how are you today? You should, I'm fine, and you? I should expect this, right? So also we need to build the data set for training. We need to convert this one into numbers, using these numbers for training the model. In natural language processing, there is something called word embedding. And word embedding is something similar to the autoencoder, right? Because I have those 10,000. Those 10,000, when you look into numbers, it's most of the values are zeros. So it's not efficient, in fact, to use this very huge matrix or vector, 10,000 values. So word embedding means we try to also compress this one into a code, like input encoder. So the input will be this 10,000, and I can decide the length of the code. We need 10 values, 20 values, 64 values, and it will be float numbers. So in this case, I will convert this 10,000 into a shorter code, which can be used for simplifying the word. We call it word embedding. We will talk about it later on. So, so number of parameters, it will be this number of 10 million for this simple model, and that is for this one, it overfits. It's 10 million, it's too much, 10 million, right? And maybe the data set is 50K, it's not enough. I'm using 30K for training and 20K for testing. So maybe it's not enough data for training the model. I'll show you the first 4 epochs, because this one go for overfitting quickly. If I will continue training it, I use the early stopping here. I don't know if I use it here or not, but maybe the version which I use the early stopping. Because this one go for overfit. When you train it for 10 epoch, you can see clearly that it overfit my data, right? So I use the early stop to stop it, right? Do you have any question in this? So the output here will be, the dense layer here, we have 2 outputs, right? Number of parameters here, it will be 2 times 64 plus 2, right? So it will be 128 plus 2, it will be 130. So the output, we have 2 outputs. The output will be 1 and 0. So, yes. Last one, it's binary classification, right? This internet movie database that was binary classification, so we have posted and negative. If we need to use an example for multi-class classifications, we can use this Reuters dataset, and it's news wires, and their topics published by Reuters in 1986. It's the same also we have in those news wires. So it's like a text and a topic. Which topic? Maybe this is in politics, economy, and stuff like this, foreign affairs, and so on. And it uses for text classification, and it consists of 46 topics. So we have 46 topics, where some topics are more represented than others. It's not they call it non-balanced data sets. You will face this one all the time. Sometimes you will have this kind of unbalanced data sets. It's a problem. Because if you will train a model using unbalanced data set, the model will be biased, right? Correct. So if I trained a model with this reviews and most of the reviews are positive, it will be biased towards positive reviews. It will be hard for the model to discover those negative reviews because the data set is unbalanced. So there are many ways for fixing this unbalanced data set. So each topic has at least 10 examples in the training set. So the data consists of 8,982 training examples, and this number for testing examples, right? So it will be also like this one. So this is, for example, this is Newswire. It will be something like this one, and well, it's the same. Also, the size will be different, right? Because some how do you call it, reporters or something, they maybe some events are important. We elaborate, some others are very short, so the size will be different. So we would also select the most popular 10,000 words, from those news wires, and I will build a dictionary. I will give an index to each word. I will convert to this one. I will replace each word into its index, so it will be the same like this one. The size of this one exactly the same as this one, because this one is just as an index, right? So I have this index. I need to convert this one into something fixed size. So I will use 10,000 values vector for representing each news wire. It will be the same, right? It will be zeros and 1 when exactly when the index, except 1 at this index. So I have the problem here 2 and 2. So this word is deleted twice. So we can just write 2 because it has been repeated twice, and at the end we will normalize the procedure. We need to check this. It will make difference. The end topic index here it's 3, so this is output effect. So the output will be a vector of 46 values, and it will be zeros everywhere except at the topic, because the index topic is 3. So it's 0, 1, 2, 3. Right? So it will be 1 here. The rest will be zeros. So we have here, so the one in the background, in fact, you see the one in the background, this is the 10,000 values. This is the input vector, right? And the output will be 46 values, this one. And we will use it for building our model and training our model. So the model, how the model will look like, you just, I used here 1, 2, 3, this is just 3 layers. I just use 3 layers, and I don't know what was the accuracy. So, so the input will be 10,000. Input shape will be 10,000. Number of neurons here, it will be 128. The second one, the input will be 128. The output will be 32. I used and the output will be 46 because we have 46 topics, right? We have 46 topics, and this is the number of parameters. It's also we will have 1 million, more than 1 million parameters, which is too much for the dataset which you have, because the dataset is also very small. So I guess I don't know if I used here the hairless topic, but we can check. So it will be like this one, and you can see here, you just discover it. This is a training and validation loss. So this is a training loss was decreasing, right? And this is the validation. So the validation loss was decreasing, but still decreasing, it's fine. I guess we don't have any overfitting here, right? It looks okay. Both are decreasing. So maybe we need to just, if we will have flat point, how do you call it? So if this one starts going up, for example, we can say that not this one. This one, it will be, this one will go down all time. So don't need to look into the training, because the training will go down all time, even if you are overfitting, right? When you are overfitting, the model will memorize your training data set, and the performance will be fantastic for the training data set. But for the validation, if you can see that this one will go up again, it means you will start overfit.
Validation is the line.
Hmm?
Validation is the line, not the dots.
Okay. Yeah. So this is a training loss. Training loss goes down. Yes, and this one is, yeah, it's still. Look. Yeah. All right. Maybe we need to train more to discover if we will have overfitting or not. So, for example, here training and validation accuracy. We can see it also from here. It's the training accuracy still goes up. Validation, it still goes up. If this one starts going down, we can see that we have overfitting, right? As I told you, overfitting. I try to plot confusion matrix, but we have 46 classes, so it's impossible to plot this confusion matrix in fact. But so those examples, it's examples for images. Example for text, because it's very important. Maybe at some point we need to work with text. So we need to understand really how can we work. I wish also if some of you can start working with a video, for example. It would be nice. If we can track a person in videos, right? It would be very, very good. Or an animal, for example. It's very useful, in fact. Because I know some guy, he is working in Nover, and he working in this the farm for bits. What is the name of the farm? What? Barley, yes, it's a barley for this bigs. And he put camera because bigs, you try to understand the behavior of bigs. Because sometimes there are bigs which are very aggressive. And you need to train, and you need to know which one is aggressive and to take it out. And so he tried to use machine learning for building a model to understand the behavior of bigs. So it has camera, which has images all time, and they learn from the behavior of bits, and they track it in different. He tracks it because in the barn you have multiple bits in the same place, right? And they find they bite each other or something. So he wants to identify which one is making the problems and troublemaker. So you want to track that animal in different. You can just make this and say, okay, this one we made this example. They don't want to go back in a video for 10 hours and check which one was doing what. It's impossible, right? So they want to find which one. So you can train models, multi-phase, multi-pass, number of the big example, for example. And they give you the ID for each one, for example. You can just have behavioral model, or you can build a model which can give you a reporting. Text model. Because if we can train a model for sequence, the input will be an image and the output 1 to sequence. What is 1 to sequence? The input will be an image for a video, and the output will be a text describing the behavior of the video. I can build a data set. We will have a video for a pig. Oh no, this is a good boy. He's doing well, right? So you can build a data set and train a model, and the model will have this approach 1 to sequence. The input will be an image or a sequence of images, and the output will be a description. What has been done during the last day, for example. Right? So you can get this report automatically, in fact. So the machine will give you a report each day, for example, what has been done. This one was good boy, this one was bad, aggressive, something like this. Okay, so convolutional neural network, CNN, I guess we are okay with this one now. So it's it learn higher order features in the data using convolutions. So the idea is to understand or to get some higher order features. So convolutional layer is responsible for systematic application of one or more filters to the input. We have the input, we have a filter, and we will apply this filter to the whole image. We will scan the image using this filter. How many filters? Number of filters will be a number of feature maps, right? This size will be the same as the size will be different, will shrink, right? So we need to know how can we fix this. How can we fix this one? Why is the feature map will shrink? The feature map here will be the same size as this one?
Because of filter.
Because of the filter,
Yeah.
will
And
shrink.
then you can add some zero value.
So yes, so padding is very important. If you need to keep the same size, we need to add zero value. Correct? So because how can the output will shrink? So imagine we have an image like this one. In fact, when we apply this filter, we're not applying it from here, we will apply it from, so it will be like this one, right? Correct? So we can apply it like this one. And this is no problem. So it will be yes, it will be something like this one, right? So yes. So it will be like this one. So in this case, in fact, we are not doing it. But I mean, if you will use zero padding, it will be like this one. But we are not using it. We are just putting it like this one. So in this case, we will make this convolution and the equation, and we will put a value here. So we are losing, in fact, one row and one column in this case. So the output will be one column and one column from above, one column from the right. And when we reach this one, we will lose also one from here. When we go bottom, we will lose one from here. So it will be 2 minus, so the size, if this size s times s, this one will be s minus 2 times s times 2. So it will shrink if you are not using value, zero value, right? Correct? If the kernel is 3 times 3, if it's 5 times 5, 5, we will lose 2. We will lose 4 column and 4 rows. Correct? If it's 5 times 5. So it will shrink all time, it will shrink 1 because of the convolution. Right? If you want to avoid this, we need to add number of rows on top and from each side. It's according to the kernel size. Right? If you are using 3 times 3, we will add one on top, one bottom, one column left, one column right. If it's 5 times 5, we need to add 2, 2, 2, right? To keep the same size. Why it's important? It's important because you know, when we apply convolution, what will happen? The part in the middle here will be scanned several times. Correct? I mean, this part here, it will be scanned a lot. Not that part. Not edges. We will scan edges very few times, in fact. But the part which will be scanned a lot, the part in the middle. if you have important information in the edges and you are worried that this information will be lost, in this case, we need to use zero banding. It's important in some, of course, we know that in each image, maybe the information in the center, this is the most important. But in some other application, information in edges, it's extremely important, right? An example, if you have an autonomous car, you have the, maybe an autonomous car, the most important is edges, correct? Of course, all is important, but edges, information at the edges are important to avoid accidents. Maybe a car coming from one side quickly, and if you look into the camera, for example, you will see it as an image for the first time. So you need to make the decision, should I stop or should I continue driving? For example, there is animal crossing the road, for example, it will start from one side of the image to the other side. You don't want to decide, you don't want to wait until the animal is in the middle of the image and make decision, right? You need to be proactive. So once the animal is jumping, once you feel something coming from one edges, you need to make decisions and to be proactive and make decisions as much as possible. And for example, make right? So sometimes, if we will not use zero banding here, we will lose information from edges. Or not only, we are not paying attention to the information coming from the edges, we will lose something here. If it is very, very important, in this case, we need to add zero banding to keep all information in the edges of the image. So, so we will yes. So we will have a number of feature maps. We can use max boolean, for example, or boolean bool feature maps. So the size will be shrinked a lot, right? This one, it's like summation, it's like some summing or doing some summarization, for example, shrinking, yes. And after that, we will apply another convolution layer. So the input will be those feature maps. And we need to decide how many feature maps also. We need to decide the kernel size. Maybe the kernel size will be the same as this one, maybe it's different. Max boolean again, and so on until we finish. So when we finish here, we will have some feature maps. Those feature maps, we need to flatten them and connect them to a fully connected layer or a number of fully connected layers. The fully connected layers, this is the shallow part which make decision, right? So when we build a shallow learning model for any data set, we assume that we have been working already with the features and you extracted some features. But in deep learning, we will just use a top part here for feature extraction. At the end here, we will have some very nice features, feature maps. We will use those feature maps for decision making. So in fact, in transfer learning, this part is complex to train. In fact, we need more data to train, right? This is a complex part. So I can just import the part from any model, from AlexNet, from VGG16, from Master RCNN, pre-trained model or something, right? Or Euro or whatever. And I will use this one because some people has been trained with this for image classification, for example, in AlexNet. In AlexNet, we have how many classes? 100? How many classes in AlexNet? So AlexNet, it has been trained using millions of images. So the first part of AlexNet, it's the one for feature extraction. Now I'm working in machine vision problems, so it's the same because it's image and it's object, right? Each image is the same. It's just maybe different object, whatever. So I can just use the one from AlexNet and I will apply it to my raw data and it will extract very nice features, right? And once I have those nice features here, I will design that part according to my problem. In AlexNet, we have different number of classes, different problems. Now I have different problem, so I will design that part according to my problem. So I will import this one from AlexNet or from VGG16, VGG19, or whatever, and I will design that part for fully connected layer. The weights here, it will be initialized from initial values, random values, and I will train the model, but I will frozen that part.
Yeah.
We don't need to train it again because it has been trained. If you will train it again, you will destroy all those weights. So you will just like someone who started from scratch. No, don't start from scratch. Want to train the part, don't touch it. Because this one has been already trained in very huge GPUs for many hours, many weeks, in huge data sets. So just use it as it is. We import it because this part is very clever in extracting features. And I will play with those high level features here. And I will design new part here for my model. I will freeze those weights. I will not train it again, and I will train the whole model using my small data set. Correct?
Yeah.
So
And the last section, the last layer works like a classifier.
yes, this is a classifier.
Yeah.
So on LXNet, we have maybe hundreds of classes, but my problem now is 10 classes, and I'm using it for MNest. We have 10 classes. So I need to build this one for my own problem. All those weights here will be initialized from random values, but number here will be limited, correct? So I can just, using my limited set, I can use it for training those fully connected layers. So now we are safe. And we save lots of time because I don't need to start from scratch. So I advise you also, if you are working in any kind of problems, try to play with those pre-trained models first. So the fully connected layer, this is the one which will be used for classification. So the building blocks of a convolutional layer, it's 3 types. We have convolutional layers, we have pooling layers, we have fully connected layers. Right? We have convolutional layers, pooling layers, fully connected layers. In the convolutional layers, we have filters and feature maps. So we need to define how many features you want and what is the size of your feature kernel size. You need to define it. Right? Kernel size, it's hyperparameters. All those are hyperparameters. So there is no rule, in fact, for selecting. No one can say 32 is better than 46. Oh, you need to try it. So all those are hyperparameters. Filters are essentially the neurons of the layer. Each filter is a neuron, right? We will have weighted sum activation. So each filter will do this. Weighted sum and activation. When you have more feature maps, it means you will have more activations, more processing. So it will take more time. If you want to reduce time, try to reduce number of features. If you want to reduce time, increase the feature size, right? Because when you increase the feature size and increase the stride, maybe you will have less number of activations, right? With the stride. They have both weighted input and they generate the output like a neuron. The input size is a fixed square called batch or receptive field. It has a receptive field, in fact. We're just looking like this. If the convolutional layer is an input layer, then the input batch will be pixel values. Inputs will be pixel values, right? If they deeper in the network architecture, then the convolutional layer will take the input from feature map. Yes, if it's deep. So for the first convolutional layer, we are working with the original image. The second one will be working with the feature maps, right? So it's only the input layer will deal with the original image. The rest will be working with the feature maps. So the feature map is the output of one filter applied to the previous layer. A given filter is drawn across the entire layer, moved 1 pixel at a time, moved 1 pixel or 2 or 3, so according to stride size. Right? Each position results in an activation of the neuron, and the output, the output to collected in the feature map. The output will be collected in the feature map. So we will apply this one to the receptive field, and the output will be applied to the feature map. Right? If the receptive field is moved 1 pixel from activation to activation, then the field widths overlap with the previous activation by field size -1. Correct? So if this one 3 times 3, and the stride is 1, so there will be overlap by 2. Correct? Because if this one it's 3 times 3, stride equal 1, so overlap will be how much overlap? 2 pixels. It will be 3 minus 1. Correct?
Yes.
So, yes. So the distance is that the filter is moved across the input from the previous layer. Each activation is referred as stride. Zero padding is used to invent mock inputs with 0 values for the receptive field, not to read off the edge of the input feature map. We don't need to ignore the edges. So in this case, we can just use 0 padding. Yes, it's just how convolutional is done. So we just have this input. This is a kernel 2 times 2. So this is the question. If it is 1 times 1, what will happen? Right? it is 1 times 1. So it will be just this one multiplied by this one. Applying it to activate, maybe because we will apply it to the activation function. Anyway, the output will be different. The output will not be the same because we are not just, but if you are using linear activation function, the output will be the same. Correct? So if you are using kernel size 1 times 1, and you are using linear activation function, we even are even new because the pixel value will make supposed to values. So the input will be the output, right? So what would be the value? Maybe in math RCML, because they divide the image into sections, maybe they need to divide, maybe they will use it for dividing the image into sections, right? But this is how it works. So we will apply this kernel into that part, right? So just multiply this value by this value, this one by this one, this one by this one, this one by this one, summing plus bias, and send this value to the activation, and you will get a value, apply it to the first pixel of the feature map, and just move one step.
Dot product.
Hmm?
That is the scalar product.
Yes. It's called what?
The scalar product.
Scalar product.
Yeah.
Yes. Yeah, correct. So it's just 1 times scalar product,
Because
but
you need one.
value.
Yeah.
Yes, it's a scalar value, correct. Scalar value. But remember the bias.
Yes.
So it's omega x times, so it's omega, which are the weights here, multiplied by the receptive field plus bias, and applying the activation function, right? So, so this one would be 0 when applying it here, for example. So all 0 except it will be 3, right? When we apply here, it will be 1 times 2 plus 2 times 3, 6 plus 2, it will be 8, and we can just go. So zero padding, when applying convolutional layers, we lose some pixel around the perimeter of the input image.
I have a question. When you are using the scalar product, there is an angle between the two vectors, the first one and the kernel. And for this angle is always fixed, or you can change it in order to get better result.
No, you cannot change it. If you want to put it as a scalar, as a vector.
Yeah.
So what is the dimension? So this one, imagine it's 4-dimensional.
Yes.
We have 4 values, right? If you will put it as a scalar, imagine it's 3 values.
Yes.
Or 2 values, can make it 2 values. So it will be a vector. So imagine I'm using because we need to plot it in 4-dimensional space and cannot. So imagine it's 2 values, right?
Yeah.
So it will be, imagine I have those 2 pixel values. So it's 1 and 2, for example,
Yeah.
right?
Yeah.
So this one will be 1, this one will be 2.
Yes.
So this is a vector.
Yes.
We can call this is a receptive field.
Yeah.
We need to look into the weights, omega 1 and omega 2. So those omega, maybe it's something like small values or something like this one, right? Maybe it's something like this one. So I mean each update, those omega values will change. So the angle will change. But for the original image, it's fixed because it's fixed. It's the original image. For the input image, it's fixed.
Yeah, I got. Yes.
But for the picture map, it's different because each time you update, right? So the vector, I mean, for the original image, if this one is the original image, it's fixed both times in each iteration. But the picture map will be different because each time we apply this one here, this one will be different. So the vector here will move, in fact, for the picture map. Each time it will be different values because we're updating, and also the weight will be different each time. But if you're applying it to the input image, this is fixed both times.
Yeah.
So zero padding, when we apply the convolutional layers, we lose some pixels around the perimeter of the input image. It can add up for successive convolutional layers. One solution is to add pixels of zeros. We just add those. We know now what is the meaning of those padding. Stride by default, the filter slides 1 pixel at a time. You need to know this 1% because stride, when you didn't specify stride, it's 1.
Yeah.
So you have stride.
Yeah.
Because in your example, you just say we don't have stride here.
Yeah.
No, just remember that you have stride. By default, it's 1. Because we have to move. By default, we will move by 1 step. If we didn't specify instant. So in your example, you need to select stride equal 2, for example, and compare between model API and sequential and so on. Really, is there any difference?
The functional API use the straight with one.
With one.
Yeah.
But you use max pooling,
Yes.
right?
Yeah, I know.
Yeah. And the only
But then, for example, you can combine and mix both of them together. You can remove max pooling and uses the stride as a parameter in the HTML.
also max pooling is important because if you don't use max pooling, we will keep the feature map the same size all time. And in fact, people usually try to reduce the size of the feature map when we are getting closer to the full connected layer.
Yes.
So this one will not remove the other one, right? So max pooling will shrink the feature map.
It's about the
But-
size of the kernel. Yeah.
No,
Map.
feature map.
Yeah, feature map.
So I will start with this feature map, and I want to end with this one before fully connected layer because I want to reduce number of weights here.
Yeah.
So I need to make this one less. So we can use max pooling several times to reduce this feature map size.
Yeah.
If you don't use max pooling, you will have the same. And instead of having a model with 1 million, it will be 2 million weights. Because of this, so max pooling is very, very important to reduce model complexity. So
Yes.
models will not overfit.
Max pooling is related to the size.
Yes, it's
And
about
the
the size.
size is about how to step over that size.
Yes, correct. And how you step over, how you
Yeah.
slide will impact number of calculations
Yes.
and time used for training your model.
Yeah, exactly.
So when you want to compare between the models, you need to fix all the model structure.
Yes.
If you are using here max pooling, you need to use here max pooling and run both of them and see if there will be a difference in running time.
Yes.
Mhm.
We will do.
Yes. Building blocks of CNN. So max pooling, this is how max pooling is working. So it does not have any parameters, right? If it's max pooling, for example, 2 times 2, so we will start here, right? And we will just select max. What is the max of those 4 values? It's called max pooling. Could be average, right? If it's max pooling, I will just select this is the max. I will put it here in the feature map, in the expected place in the feature map. I will move here. Or if you are moving with a stride, so we will see what is the maximum value, and so on. So it will shrink, it will reduce the size a lot, right? So it will be if I will move one step, what will be the maximum of this one? It's 5. I will go here, what is the maximum? 7. I will move here, what is the maximum? Is 8. So it could be max pooling, and it could be also average pooling, right? So the pooling layers, down sample, it's down sample the previous layers feature map. Pooling layers follow a sequence of 1 or more convolutional layers and are intended to consolidate the feature learned and expressed in the previous layer feature map. They compress or generalize feature representation and generally reduce overfitting of the training data by SML. So it's consolidation, in fact, make some consolidations and down sampling, right? To generate more general feature maps. And they have also receptive field, often much smaller than the convolutional layers. Usually, of course, it must be because we are down sampling. And also the stride or number of inputs that the receptive field is moved for each activation is often equal to the size of the receptive field to avoid any overlap. So I don't know, is it the stride equal the size of the max pooling? It should be 2, so we can not overlap. I don't know. We need to check this. Pooling layers are often very simple, taking the average or the maximum of the input value in order to create its own feature map. You can invent a new approach here. So now we have maximum, we have average. It could be a linear combination, right? Really, it could be a paper. We have 4 values. We need to compress those values into a single value. So you can train a model for it, right? How can you calculate this? So it could be, for example, 2 times this one minus this one plus this one minus this one divided by n. You can find a linear combination to create another value and come up with a new method, a new approach. Because now we are using only 2 approaches, maximum and the average, right? So you can find a way to make it different. And if this way of this approach works better, So it will be
You are talking about how to product the filter and that section of filter.
no. I mean this max boolean. We have to approach now max and average. So if you can invent a new approach here, it will be a new approach, right? Because we will have been testing the average and the maximum. Is there any other way for doing it? Right? I have 4 values and I need to combine them into a single value. How can we do this? So it could be something here, we can do something here, and we can develop a new algorithm for something. So they have so Boolean layers are often very simple, taking the average or maximum of the input value in order to create its own features. So maybe we need to go faster. I don't know what time is it. Are you tired? Do you want to take a break or something?
That's it. That's all.
The class is almost over.
Okay. So we will just finish soon because each time we're just.
Yeah, just
The class is in the blink of an eye. Imagine.
Yes. So this is the building blocks. Fully connected. What is the fully connected layers? We have just we have this is the input volume. Input volume. This is input image. Some people they call it volume. Input volume. So we have some convolutional layers. We strive. We have the max pooling. So finally here we will have a feature map. We will flatten this feature map. This is how we flatten it. We just convert it into 1D vector, right? Because for the fully connected layer, we just need to connect each value with a value. And you select your fully connected layers. It could be 1 layer, 2 layers. The output will be, of course, number of classes, right? And just obtain the model. So fully connected layers are the normal, flat, feed-forward, and neural network layer. These layers may have non-linear activation function or softmax activation function. Usually, I mean, this one will be, for example, ReLU, this one will be softmax, right? ReLU, because in fact, we are still working with a pixel value. So this one should be ReLU. This one will be softmax, because when it's softmax, we can just get probability of classes. These layers may have nonlinear activation function or softmax activation in order to output probabilities of class predictions. Fully connected layers are used at the end of the neural network after feature extraction and the consolidations has been performed by the convolutional and the Boolean layers. They are used to create final nonlinear combinations of features and for making the predictions by the network. So this is the last step, last layer. We just make decision here. We can just classify. This image, it's cat and the dog, for example, if we have 2 classes. So, I mean, before finishing, we can just talk about Keras. Keras provide an implementation of convolutional layer, Conv2D and the Conv3D. Is it in Conv3D? When the image is it's 3 channels, or just it's Conv2D, right?
Exists. Exists. It exists.
Exists. Conv3D.
I haven't seen it. We use that one.
Okay. It requires the expected shape of the input image in terms of rows, height, column, width, and the channel's depth. So maybe when it's a 3D, when it's RGB image, and you define the kernel size by 3 times 3, you need to define 3 times 3 times 3, right? The filter contains weights. So this is the filter size. Now the input image, it will be rows times column, height, width, times number of channels. The filter contains the weights that must be learned during the training of the layer. The filter weights represent the structure of the filters that the filter will detect, and the strength of the activation indicates the degree to which the feature will detect. You just need to define number of filters and the shape of the filter. We need to define the size and number of feature maps. So this is the implementation. In fact, we did that already in some examples. So if you will go for sequential, you need to define dense layer, for example. You need to define number of units and the activation and the dimension of input, right? So and after that, after building your model, you can just compile your model. You need to define the loss function. You need to define the optimizer, and you need to define the accuracy metrics, evaluation metrics. And after that, you need to fit your model using your training data set. You can fit your model using the training and the validation also. You can define the validation set for validating your model. And after that, you will evaluate your model And after evaluating your model, you will use your model for prediction. So because Ricardo is outside, so we will finish here. I have been talking about some filters, how filters works in fact, because those features is something, filters, we inherited them from image processing. So sometimes you have an image and you want to detect edges, for example, is it vertical, is it horizontal edges? So we use those filters, but in deep, we will train those filters by data, right? Because for example, if I have an image, for example, I want to detect this vertical edges, for example, right? So I can use the filter of this one. It will detect it. Now I have an edge here, correct? So we can detect it. So the whole image will be black, and it will be white at those vertical edges. So we can apply each filter. Imagine this filter has those values. You apply it to the image. You will detect some edges, for example, in the image. And you can invent any kind of filter. You apply it to the image. In neural network, what we are doing, we just initialize those values by random values, and it trains those values. Just call this one omega 1, omega 2, 3, 4, 5, 6, 7. Initialize it with random numbers, and it trains the model to get the most appropriate values for detecting some use from the image. So you don't need to specify anything. You just need to specify number of filters, and the model itself will try to learn those weights, which will make something, which will try to predict features which has a meaning for my problem. So we will stop here because Ricardo is outside, and we will meet again next week. So the plan next week, please. I guess we have something today. Some people will present something next week. Yula, I guess you will. You can present something. Okay. Okay. So just to prepare something, and also for people online, you can just, if you have something to present next week for your project, just please prepare this, and just you are welcome to present the progress in your project, so we can discuss it and we can provide feedback to all people in their projects. Okay. So some fact for you.